Students, in this video we will be looking at polar plots and how to draw polar plot for a given transfer function. So polar plot is a plot drawn between magnitude of g of j omega and phase angle of g of j omega for various values of omega. That is, omega is varied from 0 to infinity. This plot is also called as a Nyquist plot, and it is drawn on a polar graph sheet. Okay, let me show you a polar graph sheet. So your polar graph sheet will look like this. I hope students are having by this time they are having polar graph sheet with them. Okay, this graph sheet contains two things. One is radial lines, and another one is, these are the radial lines. Okay, these are the radial lines, and you have concentric circles. You can see circles, am I right? So you have radial lines and concentric circles. These radial lines represents the phase angle. Okay, in clockwise direction it goes in the negative, minus 10 degree, minus 20, minus 30, minus 40. In anti-clockwise direction it goes in the positive, that is, this line will be 10-degree line, 20-degree line, 30-degree. Either you can say that as 10 degree or minus 350, both are same. Similarly here also, either it is minus 10 degree or plus 350 degree. So here radial lines represents the phase angle. Okay, so every 10 degree the line is given. Suppose if it is minus 15, so that line will be lying between this minus 10 and minus 20, somewhere here. Okay, that will be your minus 15. And this concentric circles scaling we have to do. Okay, every circle represents a magnitude, so we have to scale up. Okay, so every 10 circles, for example, if I take the center as 0, then at the 10th circle if I am taking it as 0.5, then every circle is how much? 0.05. It will be the magnitude of every circle. Okay, so the first circle will be 0.05, and the next one will be zero point 0.1, and the next circle will be 0.15, and next one will be your 0.2, 0.2, and next will be your 0.25. The next concentric circle, this circle will be 0.3, next will be 0.35, 0.4, 0.45, and 0.5. This line will be 0.5. So any point on this circle will have a magnitude of 0.5. Okay, so like this, if you continue 0.5, this is your 1, then this is your 1. This circle is called as a unity circle because the magnitude of this particular circle is 1, unity. So make it slightly thicker. Okay, uh, according to your scaling, this unity circle may lie here also. Suppose some other student has taken this as 0 and this particular 10th line as a 1, then for them this line will be your unity. Okay, unity circle. So now the scaling in this particular plot, I have taken it as 0, 0.5, 1, 1.5, 2. Okay, just a briefing about the polar graph sheet. That is, it has radial lines which representing the phase angle, and the concentric circles giving the magnitude. It represents the magnitude. So that means that any point on this graph sheet will have two things. One is magnitude and another one is phase. Okay, see, before we go into explaining the gain margin and phase margin from the polar plot, let us draw a polar plot from this problem. Okay, so for this open loop transfer function, we are going to draw the polar plot and then enter into the computation of gain margin and phase margin. So you can see that this is in the standard format: 1 plus s into a constant, 1 plus s into a constant. So first thing is you have to substitute instead of s j omega. You will get g of j omega. Okay. Then you have to convert this g of j omega into magnitude and phase. Before that, we have to find the corner frequencies. The corner frequencies are 1 by 2 and 1 by 1. That is 0.5 radians per second and 1 radians per second. A small change from Bode plot is you need not find magnitude in decibels. Just find the magnitude, that is enough. That means 20 log need not be operated. Okay, so the magnitude will be in numbers, but it will not be in decibels. Okay, so 20 log is not given here. So how to find the magnitude of j omega is omega, and phase of j in the denominator will be minus 90 degree. Magnitude for this term is square root of 1 plus omega square. Magnitude for this term will be square root of 1 plus 4 omega square. So phase angle is tan inverse of omega by 1, tan inverse of 2 omega by 1. The negative sign because it's in the denominator. So after getting the magnitude and phase, okay, phase expressions, for various frequencies you have to obtain the magnitude and phase. Here I have made it as a single table because you will understand why. Okay, here you need not make it as like two different tables, one for magnitude and another one for phase. For every frequency you should have a magnitude and phase. For every frequency you should have a magnitude and phase. So I have made it as a single table. The selection of frequency surely should have 0.5 and 1 radians. So here is 0.5 and 1 radians. You can select some frequencies in between 0.5 and 1 and something lesser than this 0.5, and sometimes even you can choose greater than 1. Okay, so this is my selection. For every frequency you have to find the magnitude and phase. So substitute 0.35 here, 0.35, 0.35, find the magnitude. Here also 0.35, 0.35, and find the phase. So for every frequency point omega, you have to find the magnitude and phase. After computing this entire table, now let us move on to the polar graph sheet and plot all these points there. Okay. So now let us start with this point. For 0.35 radians per second, magnitude is 2.2 and phase is minus 144. So now you have to look into the scaling is, as I said, the scaling for the magnitude is the center of the white space is 0, and this circle is given the magnitude 0.5. This circle is given 1. That means you can find for every circle in between what is the magnitude. Okay, so this is 1.5 and this is 2. So our magnitude here is 2.2. Am I right? So you have to find which circle is 2.2. I think this circle is 2.2. Right, this circle is of magnitude 2.2. So magnitude is 2.2. So the entire circle, everywhere on this magnitude graph, the it will be magnitude will be 2.2. But we have to find a point at minus 144. Where is minus 144? Here the line is minus 130. Here it is minus 140, and here it is minus 150. So minus 144 will be somewhere between minus 140 and minus 150. It will not be at the center, slightly below the center. So this here in this line, radial line, you will have minus 144. So this is the point where minus 144 and the magnitude is 2.2. The magnitude is 2.2. So this is magnitude 2.2 and phase minus 144. So mark that point, and besides that point you please write your omega as 0.35. So similarly you continue with the next point. What is the next point? 0.4 radians per second, 1.8 and minus 150. Minus 150. So now it's very simple. This radial line is minus 150. Okay. 1 point, and you have to find the magnitude is 1.8. Which concentric circle is 1.8? I think this circle. So this circle, come down here, this point is minus 150 and and 1.8. Am I right? 1.8. So mark it and write besides the point omega is equal to 0.4. So can you continue like this? So the next point, I think 1.5 and minus 156. So this particular point is plotted. Similarly, you plot all other points, okay, and after getting plotted all the points, join it just join it, okay. So this will be your polar plot. This will be your polar plot. It is very simple actually. If you practice it on the graph sheet, it's very simple, okay. So now after drawing this polar plot, how to get gain margin and phase margin? See, actually in polar plot, it is very easy to get gain margin and phase margin compared to your Bode plot. Okay. So let me explain with a model graph here and then move on to the actual graph. Okay. Suppose this line is your polar plot. Okay. If this line is your polar plot, gain margin is got by, see now gain margin will not be in decibels, okay. It will not be in decibels as we have done in the Bode plot. It will not be in decibels, simply it will be a magnitude, okay. So gain margin is nothing but you have to find at which point this polar plot cuts the minus 180-degree line. This is your minus 180-degree line. This plot cuts the polar plot at this particular point, am I right, at B. So you have to find what is the gain. What is the gain at that? Gain means what is the magnitude of the concentric circle here. So if you are having the gain as some zero point 0.4, okay. If it is cutting, if through this point, a zero point 0.4 circle flows, then if it is zero point 0.4, then 1 by zero point 0.4 will be your gain margin, okay. So I will repeat it. This is the polar plot. You have to find a point where it cuts the minus 180-degree line, okay. The corresponding magnitude of the gain will be it has to be noted, and the reciprocal of it will be gain margin. That is one point. The next point is phase margin. For phase margin, you have to find where this plot cuts the unity circle. So that's what I was telling. Unity circle is of some significance. Okay, where it cuts the unity circle. Please note down that point. Okay, at that point, see what is the angle. At that point, you see what is the angle. That is 5 GC. 5 GC plus 180-degree will give phase margin. Okay. So similar thing we have done it for some other plot. Okay, the plot shape is different. Okay, here also same procedure is followed. So gain margin, how should you find the gain margin? This is the plot. This is the plot. This plot cuts the 180-degree line at this particular point. At this particular point, you have to note down what is the gain. Okay, what is the gain? 1 divided by the gain will be your gain margin. And how do you find the phase margin? You have to see this particular plot where it cuts your unity circle. So it cuts the unity circle. This is the unity circle. The plot cuts the unity circle at this particular point. So this particular point you have to find what is the phase. So this phase, okay, phase, you have to find what is the angle. That angle is 5 GC. 180-degree plus 5 GC gives your phase margin. That's it. So this is how you find the gain margin and phase margin. Now for our problem, let us find gain margin and phase margin. So our plot, you can see our plot cuts the minus 1, this is your minus 180-degree line, cuts the minus 180-degree line at this point, okay. At this point, see what is the gain. I think this gain is 0.5, okay, and this gain is unity. This line's gain is 0.7, okay. At this particular point, the gain is 0.7, 0.7. This gain, okay, from here, from center to this particular point, the gain is 0.7. So 1 by 0.7 will be 1.4286. So your gain margin is 1.43, approximately to 2 decimal points, it is 1.43. And phase margin, you have to see the plot cuts the unity circle. You can see that this plot cuts the unity circle. This is the unity circle. It cuts the unity circle at this particular point. So at this point, what is the phase angle? That is what you have to measure. Okay. So for that, you can join this point with the center. You can take a scale, you can draw a dotted line, you can come here. Approximately this line is 170, so this should be 168, so minus 168. Okay, so this phase has to be noted, phase corresponding to the intersection point where the plot and the unity circle meets. Okay, so you have noted down the phase. 5GC is minus 168, so substitute 5GC. 5GC plus 180 degree will give you the phase margin. So the phase margin is 12 degrees. So this is how you find the phase margin and gain margin from polar plot. I hope this polar plot method is easier than the Bode plot. So it's very easy. You have to note down only two things: where the curve cuts the minus 180 degree line and where the curve cuts the unity. Okay, unity circle. Two things you have to note down. Okay, and from that you can get your gain margin and phase margin. Please try in your polar graph sheet. Okay.